The circle shown has center O, circumference 144 pi, and diameters PR and QS. The length of arc PS is twice the length of arc PQ. What is the length of arc QR?
What are we solving for here, Emma?
The length of arc QR.
Yeah, the length of arc QR. Do you see length QR or arc QR here in the figure? Do you see it?
Yes.
Yeah, it's this guy right here. Basically from Q to R, right? That arc, that segment of the circle. Okay, we got to figure out what that length is. It's not super obvious how to solve this, I don't think. Now, let's talk about what we know first. We know the circumference is 144 pi. Okay, what does circumference mean? Let's talk about that first. Emma, what's that mean?
The distance around the circle.
The distance all the way around. All the way around is 144. All the way around is 144. So circumference is 144. PR and QS are diameters, which means they go through the center point here. Kind of cut the circle in half. Okay. And then we know PS is twice the length of arc PQ. So let's think about what that means. PS, arc PS, is this guy right here in green. By the way, it looks like the same length as QR, right? Doesn't it? Mm-hmm. Yeah. Probably is, right? I know it's not drawn to scale exactly, but they're darn close if they're not. I think they are. And then so PS is twice the length of PQ. Here's PQ in yellow. By the way, does PS look like it's twice the length of PQ? Does that look like that's the case?
Yes.
Roughly. Yeah.
Yeah.
I mean, it's definitely bigger. It looks like it's about twice as big. Does that make sense? Why? Like, we can actually kind of use visual estimation here.
Yes.
I mean, it's not, is it drawn to scale? Well, it says not drawn to scale, but it's darn close. It's darn close.
Yeah.
Right? Right? So look for that. I can't guarantee that everything is going to be like closely drawn to scale. I can't guarantee that, but you can kind of just use some logic and kind of see if that would be the case. So, and then that's the case here. I mean, everything's looking pretty good. Okay. So let's go back to the question, which is, what is the length of QR? Because I think we can solve this with visual estimation. What fraction of the circle does it look like QR is? What fraction of the circle?
It's a third.
It looks like a third, doesn't it?
Mm-hmm.
It looks like a third. So the right answer is probably a third of the circumference, a third of 144, isn't it?
Just 48.
It's probably answer choice B. And I got news for you. It is. It is. It is. Again, I can't guarantee it's going to work out, but so far, pretty much on all these questions, even if it's not perfectly drawn to scale, you can use visual estimation to either get rid of some of the wrong answers, if not find the right one. And it works out here. I mean, it can't be 72 or 96. Look at those. 72 is going to be half the circle. Right?
Yeah.
Right? It's not half the circle. It's just not, even if it's not like perfectly drawn to scale, it's just not half the circle, man. It's not. It's not going to be that bad. And 96 is bigger than half the circle. That's not arc QR. Does that make sense?
Yes.
Yeah. And answer choice A is probably just too small. That's going to be like a sixth of the circle, which is probably what PQ and SR are. Okay. Let's talk about the algebra. I mean, there is an algebraic way to do this. There is. Okay. We can express length PQ in terms of X, right? Some unknown length. We can call it X. Does that make sense so far?
Yes.
Okay. And then PS, that arc in green, we could express, so that's double PQ. We could express that as 2X. Does that make sense?
Yes.
Okay, great. And because these angles here are opposite each other, it's called vertical angles. Vertical angles are always equal. And also the arcs opposite those vertical angles are also going to be equal. Shouldn't surprise you, they look equal. Right? Like SR looks like PQ, of course, right? I mean, like, you can still use visual estimation here. Good heavens. That's going to be X as well. Is that clear?
Yes.
Yeah, and then QR is also going to be 2X. Hey, it looks like 2X. It is, right? Because the same thing, that's vertical, that angle there. So the arc's going to be equal as well. Okay? So if you add all those up, you get 2X plus 2X plus X plus X. Do you know what that is in terms of X? Do you have any idea?
It's like 6X.
It's going to be 6X. Yeah, absolutely. So you could say 6X equals 144 pi. Does that make sense?
Yes.
And then to solve for X, what do you do to solve for X?
Divide, or...
Yeah. Divide by what?
Divide by a 6.
Divide by 6. Divide both sides by 6. What's 144 divided by 6?
I guess 48?
No.
Well,
Punch that into the calculator.
24. There we go.
24 pi.
Oh,
right, right. And this is tricky, right? Because that's the x value. But QR, right, is not x. QR is 2x, right? Right? You see the trap there.
Yeah.
A lot of students are going to pick A. A lot of students are going to pick A. We're not looking for x. We're looking for 2x. You got to multiply by 2. Ooh. Do you see why using visual estimation actually helps you avoid that trap?
Yes.
Be careful there. That's why I love starting with it. I love starting with it.
Yeah.
And even if you do the operation, like, okay, let me do the operation. Just make sure, that your operation makes sense visually. But 24 pi is too small. That's like 1/6 of the circle. And QR is just bigger than a sixth. It's 2/6, which is 1/3. Which you saw, just looking at it, you're like, hey, it's a third. And you were right? So you can think in those terms. Mm-hmm. Any questions about that?
Nope.
Okay, great job. Catherine, Ruby, any questions about that?
No. Nope.
Okay, great. Okay, oh yeah. This is a tough-ish question. We're talking about radians here. Catherine, you are up. Go ahead and read question number 22 for us, please.
Mm-hmm. The measure of angle R is 2 pi over 3 radians. The measure of angle T is 5 pi over 12 radians, greater than the measure of angle R. What is the measure of angle T in degrees?
Oh, this is a very tough question. Catherine, how familiar are you with radians?
Not super familiar.
Yeah, that's the answer I get from most students. Like, you've heard them before, you probably studied them in class, but you didn't really understand them. That was my experience as a student, by the way. Like, I learned about them, and I knew how to, answer some of them, but I never understood what it meant. Ruby, Emma, are you guys familiar with radians or no?
Sort of, yeah.
Sort of, right? Like, that's it, right? It's like, I've seen them, I've been tested on them, don't understand them. One way, boy, we're going to talk, there's an operation here. The nice thing, you never really have to deal with radians on the SAT if you know how to turn them into degrees, right? And we can deal with this just like a unit conversion question. And there's a special operation we can do to turn any radians value into degrees. That's not a bad place to start. I do want to talk about what radians mean here, just because it's one of my pet peeves as a teacher is that nobody understands what a radian is. So I'm just going to teach that to you real quick. All right, so we've got a circle here, and I'm going to give it a radius. We'll call it R. Okay, R. And I want you to imagine that radius is a piece of red string that I'm going to lift up off the screen and place around the curvature of the circle. So there's an arc with a length of 1 radius. Does that make some sense?
Mm-hmm.
Okay. And then I'm going to connect that to the center point, and we'll get an angle here, which we can express in terms of degrees potentially. I want to express in terms of radians. Do you have any idea how many radians that angle is?
Nope.
Anybody? How many radians that angle is? I'll tell you. That's 1 radian. Because it's the angle we get formed by an arc of length 1 radius. That's a radian. That's a radian. That's all a radian is. It's a measure of an angle formed by arc of length 1 radius. Let's do it again. Does that make sense, by the way, Catherine?
Yes, it does.
Yeah.
Yes.
Okay, great. It's nice when math makes sense. Let's do it again. Here's another. I'm going to make an angle formed by an arc of length 2 radiuses. Catherine, I'll bet you can guess how many radians that angle is.
2 radians.
That's 2 radians, the one in green. Let's do it again. That's almost 180 degrees right there. Guess how many radians that angle is in yellow.
3 radians.
3 radians. And then here, it's kind of cool. I'm a little bit of a nerd, but I think it's cool. I'm going to give you a 180 degree angle. Straight line. Guess how many radians that angle is in black. That angle that's just a little bit over 3 radians. Guess how many radians that is?
Is it 4?
It's not 4. It's just a little bit bigger than 3. I'll tell you. That's pi radians. That's pi radians. Which is kind of nice, right? It shouldn't surprise you because pi is 3.14, right?
Yes.
Yeah. So pi radians is 180 degrees.
Okay, that makes sense.
Does that make some sense? Yeah.
Yeah.
Yeah, pi radians is 180 degrees. Ruby, Emma, does that make some sense why pi radians is 180 degrees?
Yes.
Yes.
Yeah, yeah. And then all the way around the circle, guess how many radians that is, Catherine? All the way around. If pi radians is 180 degrees.
Would it be 2 pi radians?
2 pi radians is 360 degrees. Absolutely. Does that make some sense?
Yes.
Yeah. And by the way, they tell this to you on that formula sheet.
Oh.
Yeah. Catherine, I want you to read the first two statements here at the bottom of the screen share. You should see that on the formula sheet. Read those last two statements.
Yes. The number of degrees of arc in a circle is 360.
Which you knew. Everybody knows that, but read the next part.
The number of radians of arc in a circle is 2 pi.
Yeah.
Or 2 radians.
Yeah. And now you understand why. Does that make some sense?
Yes.
Isn't that kind of cool? It's nice when things in math make sense. And by the way, because pi radians is 180 degrees, we can easily figure out what like half of 180 degrees is. Like half of 180 degrees is 90 degrees. That's got to be half of pi radians. So it is. 90 degrees is pi over 2 radians is 90 degrees. Does that make some sense why?
Yes,
Yeah.
it does.
And 45 degrees would be pi over 4 radians. And 60 degrees would be pi over 3 radians. That's basically getting into like why the unit circle works. And it's funny, like as a student, like I was just kind of like forced to memorize the unit circle, but I never understood why it was what it was. I kind of memorized it. But now I know what it means. Anyway, the only reason I get into that, well, I'd like students understand what radians are. Because it's not bad once you understand it. But you need to know that pi radians is 180 degrees. You need to know that to convert back and forth between radians and degrees, which is really helpful here. Because we can take all these values in radians and just turn it all into degrees, and the question's really easy. Does that make some sense?
Yes.
Okay, so let's do that. So I'm going to take the first value, turn it to degrees. So we've got 2 pi over 3 radians. And we're going to multiply it by that fraction, that unit conversion. And we want to go into degrees. So are we putting degrees in the numerator or denominator, Catherine?
In the numerator?
In the numerator. We'll put degrees in the numerator. And we're going to put radians in the denominator because the radians are going to cancel out there. Is that clear? The radians are going to cancel out and we're left with just degrees. Is that clear?
Mm-hmm.
That's why this works. Okay. So let's do it. How many degrees are there in a radian or how many radians are there in a degree? Well, as long as the values equal each other, it may not be the same number, but as long as the value of the degrees equals the value of the radians, we're good. So what are we putting for the degrees? What are we putting for the radians?
Well, for the radians, we can put 1, right?
Well, I don't know how many degrees 1 radian is. I actually don't know. I could figure it out, but I'm not certain about that. But I know
That's
how many
right.
degrees pi radians are.
180.
180. So let's do 180 degrees in the numerator and then pi radians in the denominator. Does that make sense? Well, it makes more sense to do. You could do 360 degrees divided by 2 pi radians. That would work as well. That's fine. But I think the easiest way to do is 180 divided by the degrees divided by pi radians. Does that make sense?
Yes.
Ruby, Emma, does this make sense why this is going to cancel out the radians and leave us with degrees?
Yes.
Okay. Now, I know this is kind of like scary looking, like, oh, what do I do here? I mean, we could do the arithmetic, like cancel out the pi's, we could do all that, or we could just punch into Desmos. Or this is probably the easiest way to do it, so let's do that. Boy, this simplifies so much. Let's punch it all into Desmos. All right. So, we got 2 pi divided by 3 radians. I'm not going to worry about the radians. I know they're going to cancel out and we're going to need degrees, so I'll just deal with the numbers here. Times 180 divided by pi. There we go. And do you see what that gives us?
Yes, I do.
What do they give us?
120.
120 degrees. So I'm just going to make a note of that here. That value is 120 degrees. This question is going to be so much easier once we're dealing with degrees. And then it says angle T is 5 pi over 12 radians greater than the measure of angle R, which is 120 degrees. That's still confusing. Let's turn 5 pi times 12, or sorry, 5 pi over 12 radians into degrees. So really we're just changing the radians here. That's going to be a very similar operation. It's 5 pi over 12 radians. I'm going to do that down here. 5 pi divided by 12 times that unit conversion again of 180 divided by pi. And what does that give us?
75.
75. So T, now we could reread the question. T is 75 degrees greater than the measure of angle R. This question's a lot easier to understand. Does it make sense what we're doing here?
Mhm.
Yeah. So we can literally reread the question. I would. The measure of angle R is 120 degrees. The measure of angle T is 75 degrees greater than the measure of angle R, right? So T is 75 degrees greater than 120. What's the measure of angle T?
195.
195. It's just 120 plus 75. Does that make some sense?
Yes, it does.
Terrifying looking question, but much easier if you can just convert radians to degrees. And by the way, if they gave you a question where they gave you the degrees and the answer choices were in radians, you could just convert the degrees into radians as well if you need to, using unit conversions. Does that make sense?
Yes, it does.
Okay, great. I've got a section here on the rules. I just want to show you where it is real quick. I want to reference it. Here's unit conversions, by the way. You see that there. That's converting hours and minutes. It's the same operation, right? Put the unit you want to go into the numerator, put the unit you want to go away from in the denominator. As long as the value of the minutes equals the value of hours, you're fine. Okay? And then, but specifically for radians and degrees, here it is. It's basic concept P. Do you see that? I make a note of it here as well. Do you see it on the screen share, Catherine?
Yes, I do, yeah.
Yeah, good. So pi radians is 180 degrees, in case you forget that. But even if you don't remember that, on the formula sheet, they tell you that there's 360 degrees in a circle and there's 2 pi radians in a circle. So you can use that as well. You can do 360 in the numerator and 360 degrees in the numerator and 2 pi radians in the denominator. That works as well. But to go from radians to degrees, just multiply by 180 degrees over pi radians. Or if you want to go from degrees to radians, multiply by pi radians over 180 degrees. And the unit you want to go into is going to be in the numerator. Does that make sense?
Yes,
Isn't that nice when it makes sense?
Yes.
It's really nice. So don't be too intimidated by radians. It doesn't pop up a ton on the SAT, but pops up there and it's worth knowing. Just know how to do the unit conversions and you're good. Okay. 2 more questions to go over. Then we'll talk about the game plan. But I do want to address these because these are trigonometry questions. And it does pop up in the SAT. Catherine did the last one. So Ruby, you are up. Ruby, how familiar are you with trigonometry?
Well, we've recently been doing a good amount in physics, so I'm okay.
Okay, good.
Well, it was more like last semester, so I've kind of had Christmas to not.
Okay, yeah, I got you. All you got to know is SOHCAHTOA. Really, are you familiar with SOHCAHTOA?
Yes.
That's all you got to know. We'll talk about SOHCAHTOA. But if you know SOHCAHTOA, these aren't too bad. Go ahead and read question 25 for us, please.
Okay. The side lengths of right triangle RST are given. Triangle RST is similar to triangle UVW, where S corresponds to V and T corresponds to W. What is the value of tangent W?
Oh my goodness. What are we solving for here?
We're solving for the value of tangent W.
Yeah, the tangent of W, or tan W.
Yeah.
Is what we're solving for. Okay. This is really kind of scary. There's a lot of words going on here. A lot of letters flying around. Some numbers. But like once we draw these triangles, we're going to be good. Okay. And they give us enough information to draw these triangles. So let's draw these triangles. Now, it's a right triangle. We know that. But it's not obvious like which side is like the legs or which sides of the legs and which one's the hypotenuse. But of course, we know the hypotenuse is going to be the longest side. So we know what side the hypotenuse is going to be of right triangle RST. What's the hypotenuse of that guy?
It's going to be 52.
It's got to be 52. It's the longest side. So let's see if we can draw this triangle, and then we'll draw the other one as well to make sure all the sides match up. Do you think you can draw right triangle RST?
Yes.
Yeah, great. Give it a shot. Just make sure the hypotenuse is 52. And that'll be length TR.
Okay.
All right.
Wait. For some reason, my whiteboard is still on like a past problem.
Yeah. You might need to refresh it. I can draw it if you need me to. Let me draw it. I'll draw it for you. I'm going to draw a right triangle.
Okay, thank you.
Yeah, no problem. Right triangle here. Okay, I'm just going to make sure TR is the hypotenuse, and that's 52. I'm going to start there. Okay, so it's RST, so I'll make this S right here. It's a right angle. It says SR or RS is 20, and then TS or ST is 48. Is that right? I think that's right. Is that looking good?
Yeah.
Yeah, okay. Any questions about that, anybody? Or is that making sense so far where I'm getting those values and those side lengths from?
It's making sense.
Okay, good. There's RST.
That makes sense.
So we've got to draw a triangle UVW. I'm just going to draw another right triangle here. Right below. Woo. And that's got to correspond to RST. So here's U, Here's V. Here's W. That should work. Okay. And then we don't know the side lengths exactly for this. We don't. But when we're dealing with like SOHCAHTOA, which we are here, we can just assign some values to these sides. Because we're just talking about the ratios of the sides. Does that make some sense?
Yes.
Like we can literally just assign the same values. We don't know exactly, but it's going to be the same ratios. Does that make sense?
Mm-hmm.
So I'm just going to get the same values. So I'll do that 52. I'll make that 20. And I'll make that 48. That'll work. Okay, great. We don't know if those are the exact lengths, but those are the ratios for sure. And that's all we need for sine, cosine, tangent. And we're solving for the tangent of W. Do you see angle W?
Yes.
Okay, it's this guy right here. We're solving for tangent. Let's talk about what tangent means. Well, first let's talk about sine and cosine as well. How familiar are you with SOHCAHTOA?
I'm very familiar.
Very familiar with SOHCAHTOA. Okay, great. SOHCAHTOA, you got to know this. By the way, if you're not familiar with SOHCAHTOA, you got to learn it. Okay, SOHCAHTOA is an acronym that tells you the relationship between sine, cosine, tangent. So let's talk about, I've got this on the rules real quick. Instead of writing it all out, it'll be faster if I show you where it is. There it is. Basic concept G, trigonometry. You see it on the screen share?
Yes.
Okay. So SOH is for sine, right? Sine is the opposite over the hypotenuse. Okay. Emma and Catherine, are you familiar with SOHCAHTOA as well? Is this pretty clear?
Yes. Yes.
Yeah, okay, good. And then cosine is the adjacent over the hypotenuse. That's the AH in the K.
Mm-hmm.
And then tangent is the opposite over the adjacent. Okay, is that pretty clear?
Yes.
You do have to know SOHCAHTOA, absolutely. Okay, and we're talking about tangent here, this guy. So the tangent of W is going to be the opposite, it's the OA, over the adjacent. Okay, so here's W. What side, let's start with the opposite. What side is opposite W?
VU, so 20.
So 20. Yeah, if you're unsure about the side opposite an angle, just like bisect that angle, draw a straight line, bam, and like the side that it hits is the opposite side.
Mm-hmm.
So the side opposite W is 20. So that goes in the numerator, divided by the adjacent. Some students struggle with the adjacent. Which side is the adjacent? Do you know which one's the adjacent?
It'll be VW, so 48.
48, that's the adjacent. The adjacent is just the one that's not the opposite, it's not the hypotenuse. Does that make some sense?
Mm-hmm. Yes.
Okay, so we can say the tangent of W equals 20 over 48. Does that make sense so far?
Yes.
Okay, good. Now, notice we don't see 20 over 48. We're very close to solving this. We don't see 20 over 48 in the answer choices.
Mm-hmm.
Okay, but one of those equals 20 over 48. Do you have any idea which one?
B.
I think it's going to be B. Absolutely. And if you're unsure about it, by the way, you can use Desmos once again to solve this. I want to bring that up real quick and show you. If you need to reduce fractions, punch into Desmos. So let's say we got 20 over 48. It'll give us a decimal. Okay, 0.416, whatever. I mean, you could plug in the answer choices into Desmos and see which one equals 0.416. That would work fine. Or, I think we've talked about it before, but I'm pointing out again. You see this little like button just to the left of the fraction, where it's like a box divided by a box.
Yeah.
You can press that, and that'll turn the decimal into a fraction automatically and reduce it. Booyah, 5 over 12. Answer choice B. Any questions about that?
No.
Okay, great. Any questions about that, Ruby or Emma? Or was that Ruby?
No.
Who's solving that one? I'm so sorry.
No.
Who's solving that one?
Ruby.
Ruby,
Me.
okay, yeah. Any questions then, Catherine or Emma? Sorry about that. We're good?
No.
Okay, good, good. One more thing I want to point out. The funny thing, because these triangles are similar, right? And they tell us here in the question these are similar triangles. Technically, we didn't even need to draw the second triangle. We didn't even need to draw that. Because we know, if we're solving for the tangent of W, the tangent of W is going to be the same as the tangent of T.
Oh, yeah.
Right? Right? So really, we could have stuck with just the first one, but same, if we solve for the tangent of T, which is going to be the same, we're still getting 20 over 48. I just want to point that out. Does that make some sense why I actually didn't even need to draw the second triangle here?
Yeah.
Yeah. I'd still probably do it, but you wouldn't need to. If you really understand this question, you understand how similar triangles work, you don't even need to. You can stick with the first triangle, and that's good enough. Questions?
No.
Okay. All right. One more trig question. And then we're done. Okay. Emma, go ahead and read question number 17 for us when you see it on the screen, please.
Triangle FGH is similar to triangle JKL, where angle F corresponds to angle J, and angles G and K are right angles. If sine F equals 308 over 317, what is the value of sine J?
Ooh, what are we solving for here?
I guess the value of sine J.
The value of the sine of J. Absolutely. Absolutely. Yeah. This is a funny question. This is really funny. Let's start where we started in the last question, though. Let's start by drawing these triangles. Okay? And I think we can draw FGH pretty easily. Okay? Now we're sort of like doing reverse SOHCAHTOA here, right? Because it says the sine of F is 308 over 317. Okay? And what does sine mean using SOHCAHTOA again? What does sine mean?
Opposite over hypotenuse.
Yeah, absolutely. Opposite over hypotenuse. So I'm just going to make that really clear. So sine equals the opposite over the hypotenuse. So I want you to draw a triangle here, in this case where, so it's FGH, where the side opposite of F is 308 and the hypotenuse is 317. Does that make sense?
Yes.
Okay. Oh yeah. Well, sorry. You're having trouble with the mouse, right?
Yeah.
Yeah. Let me do it. I'll draw it. Woo. Here's the triangle. Right triangle. Okay. It says angles G and K are right angles. So let's start with angle G. It's a right angle. So I'll make this F, G, H. Okay. All right, so the sine of F, the opposite of F has to be 308. So that's 308. Down here, the hypotenuse is 317. Does that make sense how I'm constructing this right triangle?
Yes.
Okay, great. We're trying to find the sine of J. So we could draw the other triangle. Technically, we don't need to, but I'm going to here. I'll show you why we don't need to here in just a minute. I'm going to do it. Make it a little smaller. So F, G, H. So we got to go J, K, L. Okay, that's all lining up. And we give it the same values, which I'm going to here. 317, 308. Does that all make sense?
Yes.
Okay. And we're trying to find the sine of J, which is this guy right here. Make sense?
Yes.
Okay. So all you do is just find the opposite and the hypotenuse of J, right? Because sine is opposite divided by hypotenuse. Okay. So let's find the sine of J. What's the opposite of J?
308.
308. What's the hypotenuse?
317.
317. What's the right answer?
0.971.
Well, look at the answer choices, because they give us the answer choices in fractions.
Oh. Oh, is it just B?
It's B. Absolutely.
Wow.
Yeah. Does that make sense?
Yeah.
Yeah, that's not too bad. Now, a couple of reasons why we actually didn't even draw this second triangle. There's two reasons. Just like in the last one, we know the sine of J is going to have to be the same as the sine of F. Is that clear?
Yes.
Because they're similar triangles. So the ratios are all going to be the same. The ratios of the sides are all the same. So we could have just found the sine of F, the opposite of F, and the hypotenuse of F. We'd get 308 over 317. Does that make sense?
Yes.
Or, if you really understood the question, they give us the sine of F in the question. Right? That's how we got these side lengths from. Or that's where we got them from. Does that make sense?
Yes.
And if you just recognized that F corresponds to J, then we know the sine of F has to equal the sine of J. Without even drawing the triangles, if we didn't need to. Does that make sense?
Yes.
This is a funny question. If you really understand it, you don't necessarily need to go through all the steps. I still recommend it. but you don't need to here if you understand it.
Okay.
Questions about this?
Nope.
Kind of a trick question, but it's still just SOHCAHTOA. So no SOHCAHTOA,
Yeah.
nor to apply SOHCAHTOA. Just ratios of sides.